Okay, so what if the biggest force that governs everything in the universe isn't gravity? What if it's actually electricity? Now, that's the wild, provocative question at the very heart of Cosmic Plasma, a pretty revolutionary book from 1981 by the Nobel laureate Hannes Alfvén. And look, this thing was not just another dusty textbook. No, it was a full-on challenge to the very foundations of astrophysics. Alfvén was basically arguing that we've completely misunderstood the cosmos. So let's dive into his electrifying vision.
Right from the get-go, in the preface of Cosmic Plasma, Alfvén lays down this simple but really powerful rule. He says, look, if you've got a theory, no matter how mathematically beautiful it is, and it conflicts with what you can actually see and measure in a lab, well, you gotta go with the observation. You trust what you see, not the elegant math. And this principle, this total commitment to real-world evidence over pure theory, it becomes the main tool he uses to take apart some of the most established ideas in cosmology.
You know, what's really interesting is that Alfvén doesn't start his cosmic argument way out in deep space. Nope. He starts it right here on Earth, with what he called a crisis in his own field of plasma physics. He saw the entire discipline as being broken, totally fractured between two camps who had completely different ideas about how you're even supposed to do science. So this conflict really boils down to two totally different ways of thinking. On one side, you had the theorists. These guys were all about clean, elegant equations. Their models looked amazing on paper, but they had almost nothing to do with the messy reality of what plasma was actually doing in the lab. It was like they were describing this perfect theoretical gas that just didn't exist. And then on the other side, you had the experimentalists. These folks were in the trenches, you know? They were observing all the weird, complicated stuff plasma really did, how it would form these strange filaments and bizarre layers that the theorists just had no explanation for.
And this huge disconnect between theory and reality, it had some pretty disastrous consequences. It all came to a head during what Alfvén called the thermonuclear crisis. See, scientists went and built these early fusion reactors based on those pristine, simplified theories. And what happened when they flipped the switch? Well, the reactors failed, spectacularly. As Alfvén himself put it, it was like the plasma itself refused to believe in the theories. It just did its own thing, behaving exactly like that messy, complex stuff they saw in the lab. And that proved pretty definitively that the elegant models weren't just wrong, they were dangerously wrong.
And this right here is the crucial point. This is the launch pad for his entire book. Alfvén asks this incredibly important question. If these theories completely failed in our own labs, where we can actually test them and see them fail, then why on earth should we trust them to describe the entire cosmos, where we can't run those tests? And that's the moment he starts applying those hard-won, messy lessons from the laboratory to, well, the biggest scale you can possibly imagine. So that critique of lab-based physics leads him directly to his core idea about the universe. He basically says, we need to stop thinking about space as this quiet, empty vacuum ruled only by gravity. Instead, we should see it as a dynamic, buzzing, alive environment that's structured and powered by these huge, invisible electrical circuits. For Alfvén, the universe wasn't some predictable gravitational clockwork. No way. It was a cosmic-scale electrical grid. Okay, so one of the most important building blocks of this electric universe is something called the filament. What's that? Well, in the lab, plasma doesn't just spread out like a uniform gas. It doesn't want to do that. It naturally pinches itself into these thin, rope-like currents. And Alfvén said, that's its fundamental state. He saw these filaments everywhere, from the small scale of an aurora shimmering in our sky, all the way up to the massive structures of nebulae. He believed these currents were literally weaving through the cosmos, carrying energy and shaping everything they touch. And then you've got another crucial piece of this cosmic circuit, the electric double layer. Now, the best way to think of this is like a battery and a particle accelerator all rolled into one. It's this super thin boundary in the plasma where a huge voltage can build up. This thing can shoot particles out at nearly the speed of light. And if that layer suddenly collapses, boom, it unleashes all that stored energy in one explosive burst. This gives you a direct physical explanation for really violent things, like solar flares. Okay, so if you've got circuits, you obviously need wires, right? And for Alfvén, those wires were what he called plasma cables. These are electric currents that flow along magnetic field lines, and they act just like cosmic power lines. They can move enormous amounts of energy from a source in one part of space to a destination in another, totally invisibly, just like the power lines running to your house. And he argued this could be the answer to how things like massive double radio sources get all of their incredible power. So when you put all of these pieces together, the filaments, the double layers, the cables, you get a picture of space that is totally different from the standard view. It's not smooth and uniform. Instead, it has what he called a cellular structure. Space is actually divided up into these different compartments by huge sheets of electric current. And each little cell can have its own unique plasma inside. Different temperatures, different densities, different magnetic fields, and it's all completely sealed off from its neighbors. So, armed with this really powerful new way of looking at plasma, Alfvén turned his attention to the biggest target of all, the most sacred idea in cosmology, the Big Bang theory itself. He was convinced that the exact same blind spots, the same preference for theory over reality that caused the thermonuclear crisis, was leading all of cosmology down the wrong path.
And he wasn't interested in just, tweaking the model a little bit here and there. No. He asked a much bigger, much more fundamental question. What if the entire Big Bang hypothesis, our whole story for how the universe began, what if it's built on a foundation of flawed assumptions that just completely ignore the most powerful forces actually at play in the cosmos?
Alfvén's case against the Big Bang had several key points. First, he pointed out that the model says the universe should be smooth and uniform on the largest scales. But that's not what we see, is it? We see massive clumps, galaxies, clusters, superclusters. It's lumpy. Second, the model depends on a constant rate of expansion, but the observations kept suggesting that this rate, well, it might not be constant at all. But here's his biggest problem with it. The model completely ignores the incredible power of plasma physics and electromagnetism. And, most importantly, it offers zero physical cause for the expansion. It just starts with a singularity, an event that is literally outside the known laws of physics.
So if he's going to tear down the Big Bang, what does he want to put in its place? Well, Alfvén was a huge champion of a model that was originally proposed by another physicist, Oscar Klein. It's called a symmetric cosmos. And the core idea is pretty simple. The universe contains equal amounts of matter and antimatter.
The building block of this symmetric universe is something he called ambiplasma. It's just a plasma made of a mix of both regular matter and antimatter. And its most important feature? Annihilation. See, when a particle of matter meets its antimatter twin, they both vanish, converting all of their mass into a massive burst of pure energy. And this process, Alfvén argued, could be the real engine that drives all the major events in the cosmos.
Okay, but wait a second. If the universe is filled with equal parts matter and antimatter, why doesn't it all just instantly annihilate itself in one giant flash? Well, this is where his cellular model of space comes back into play, and it's absolutely crucial. He suggested that those magnetic fields and electric currents that form the borders of the cosmic cells could act like an insulator. He even compared it to something called the Leidenfrost effect. You've seen this. It's how a drop of water can dance around on a hot pan, protected by a little layer of its own steam. He believed these cosmic boundary layers could do the same thing, keeping entire galaxies of matter and antimatter safely apart.
And this leads us to one of Alfvén's most powerful and, frankly, most savage critiques. He says that because the Big Bang theory doesn't explain how the expansion gets its energy, it just says it came from a singularity, it's not really doing physics. And this quote from Cosmic Plasma really sums it up. He says, "The word cosmological is used as an euphemism for supernaturally produced." Wow. I mean, for him, saying the expansion is cosmological was just a fancy, sciencey sounding way of saying it was magic, with no physical cause.
Annihilation, though? That offered a physical, testable mechanism for all of it. It could provide the mind-boggling amount of energy needed to power things like quasars. It could explain the Hubble expansion as being driven by the radiation pressure from all that matter-antimatter annihilation in the early universe. It could even explain things like gamma-ray bursts as, say, a comet made of antimatter slamming into a star made of regular matter. The point is, it was a real, physical engine, not just a mathematical concept like a singularity.
So in the end, Hannes Alfvén's cosmic plasma isn't just some forgotten fringe theory. It's a really powerful argument for a different way of doing science, one that always stays skeptical, that trusts what you can see and measure over what a theory tells you, and one that is never, ever afraid to challenge its most fundamental beliefs. And it leaves us with this huge question. If our entire understanding of the space between the stars could be wrong, what other certainties that we hold today are just waiting to be challenged?